This is your presenter Asloob Mudassar, and I am presenting slide number 34 of the course on laser physics. The question is, what are the electric and magnetic dipole allowed transitions, and what are the characteristics of the corresponding wave functions and the Hamiltonians? The answer is, the rate of spontaneous emission is denoted by capital A and is given by the reciprocal of the spontaneous lifetime, that is equal to 16n pi cube, the absolute square of mu to 1 into nu naught raised to power 3 divided by 3 epsilon naught c to the power 3 into h. The rate of spontaneous emission, that is A, will be non-zero when mu mod square is equal to 0, or mu 2 1 mod square is when absolute square of mu or equivalently absolute square of mu 2 1 are not equal to 0. That is, the spontaneous emission arises from the power radiated by the electric dipole moment of the atom, and the transition is said to be electric dipole allowed. But when mu mod square is equal to 0, the transition is said to be electric dipole forbidden. When mu mod square is equal to 0, an atom can still radiate due to its oscillating magnetic dipole moment. Such transitions are known as magnetic dipole allowed transitions. The process is usually very weak. For a two-level atom, if mu 2 1, which is defined by the integral of E into mu 2 star into u2 star into u1 into r into dv is equal to 0, and for this one you can see equation number 27.9, then mu 1 and mu 2 are either both symmetric or both antisymmetric. That is, the radial wave function u of r could be equal to u of r minus r in case of symmetric case, and in the antisymmetric case we have u of r is equal to minus u of minus r, with the transitions allowed between even parity levels and between odd parity levels respectively, and are referred to as the magnetic dipole allowed transitions. So you see that we can have the two cases were possible, that is the wave functions could be symmetric or antisymmetric. In case the wave functions are symmetric, the transitions will be even parity levels, that is will take place between even parity levels, and when we have antisymmetric wave functions, that is u of r is equal to minus u of minus r, then you know that we shall have the transitions between odd parity levels, and in both these cases we refer to them as the magnetic dipole allowed transitions. The corresponding Hamiltonian is required to possess radial symmetry, that is h naught of r is equal to h naught of minus r. This is an important condition, that the radial symmetry is required for the Hamiltonian to obey. The eigenvalue equations in an arbitrary form is given by h naught of r operating on un of r is equal to en into un of r, where en is the eigenenergy. And you know that this equation will take the form when r is replaced by minus r in the following way, that is h naught of minus r operating on u1 of minus r is equal to en into un of minus r. And you know that as we have assumed that the our Hamiltonian must have radial symmetry, we can replace h of minus r by h naught of r. So so the equation 34.2 becomes h of r operating on un of minus r is equal to un into un of minus r into en into un of minus r. That is, un of r and un of minus r are both eigenfunctions of the Hamiltonian with the same eigenvalue En. Assuming non-degenerate levels, it follows from equation 34.1 and 34.2 that un of minus r can be written as equal to plus minus un of r. The Hamiltonian possesses a radial symmetry, is regarded as invariant under inversion. each eigenstate has a definite parity, and the electric dipole transitions occur only between states of opposite parity. So for the electric dipole moment, the transitions will occur between states of opposite parity, but in the case of a magnetic dipole moment, two cases are possible. That is the transition from even parity to even parity levels when the wave function, when the radial part of the wave function is symmetric, and when the radial part of the wave function is antisymmetric, then the transitions will take place between the odd parity levels. So this was the case that we have discussed. So this is the end of slide number 34.